Hi, everyone. We're looking at our next part of the bisectors and triangles. Today, we're going to be looking at the angle bisector specifically. So let's take a look and just remember what an angle bisector is. So angle bisectors okay, these could be lines, segments, or rays that cut an angle into two equal parts. All right, so remember from segment bisectors, we had kind of a setup when we're looking at anything that's a bisect. So we talked about with segment bisectors that part one can equal to part two, because again, you're creating two equal parts here. So keep that in mind when we start using algebra involved here, when we start bringing that in to solve out your problems and your equations. So let's take a look at what we've got going on here in our picture. So first thing we need to make sure we notice are the curves or the little arcs that are inside those two spaces. Because remember, those curves, if they have the same number of little curves in there, that's telling you that those two slices of angle are congruent. So those two pieces have to be equal. Those two angles. So that means that ray BD is the angle bisector. So what this means, again, if we go back to the idea of part one equal to part two. So let's say that part one can be our angle that's kind of on top there. So angle ABD. So remember, we start at one arrow, follow it back to the vertex, and then follow it out to the other arrow. So angle ABD is congruent to, and then we do the similar thing for the other space there, the other angle. We start outside at an arrow, so C, follow it back to the vertex B, and then out to the other arrow D. So those two angles are congruent. And I'm actually going to move this down, so give me just a second. There we go. So angle ABD is congruent to angle CBD. And then we have our part two. So again, part one, part two, I can use that to now say this is where the definition of congruence comes in, because now that I know those two angles are congruent, I can say their measures are equal. So the measure of angle ABD is equal to the measure of angle CBD. And then I could use that and plug in any expressions I might have, or use it to find any missing values or measurements. So let's see how this works with what we get when we get what's called the angle bisector theorem. So specifically, the angle bisector theorem states that if a point is on the angle bisector of an angle, then it is equidistant, which again just means equal in distance, to the sides of the angle at a right angle. And remember, right angles, 90 degrees. So you're looking for those 90-degree symbols in your pictures. So remember, we're looking for that right angle box in your figures. So I have an angle bisector here. And again, how do I know that ray BF is my angle bisector? Well, first things, there's my congruent arcs, my congruent curves that are inside there. So it's cutting the angle in half. So there's my angle bisector. Now, so what that theorem is saying, any point on that angle bisector, so in this case, let's look at F. It is equidistant. If it's making a right angle to the side of the actual angle, then those two pieces are congruent, even if that point was farther out. That distance to the sides where it's making that right angle is going to be congruent. So no matter how long the angle bisector is specifically drawn, I can still extend it out and same as before. Even if I have a point out here at the place on the side of the angle where it's making a 90 degrees, a perpendicular, it's also congruent. Those two distances are still the same. So I can keep going with that figure. Any dot along that angle bisector is going to be congruent. So knowing that bit of information, let's use this and solve out our first couple of problems. So the first one we have, find the length of segment XY. So let's see where XY is in our figure. All right, so point X is on the angle bisector. So X to Y is what I am trying to find. So it needs to be congruent from that point to the other side of my angle, and there's my right angle. So those two lengths are supposed to be the same. So I should be able to take that same 7 and copy it over because they're congruent. So segment XY is congruent to segment XW. So then the length of XY, notice there's no symbol on top because no symbol again means length, is equal to XW. So then XY has to also be 7. Now let's see if we can find an angle. Now we're looking for the measure. We're going to find the measure of angle XZW. Okay, so I'm going to erase this for a moment. XZW. So again, that is the angle that starts at X, goes down to Z and out to W. So I'm looking for this angle, that section of angle right there. So again, if XZ is an angle bisector, then either side of that angle bisector can be congruent. So just like finding XY, if I know one side of the angle bisector is making 41 degrees, so is the other. So then we're looking at angle XZY is congruent to angle XZW. So that means their measures have to be equal. So the measure of angle XZY is equal to the measure of angle XZW. So if XZY is 41 degrees, then so is the measure of angle XZW. Okay, because again, they are in congruent angle positions. So then the two angles have to have the same measure. All right. Now let's check out example 2. Ray MR is the angle bisector. So just knowing that bit of information, just knowing that, I can use that to find my two congruent parts of an angle here. So in MP is the angle being bisected. And it said ray MR is the bisector. So either side of that ray, where angle 1 and angle 2 are, they are congruent, or in this case, they're going to be equal. So then if angle 1 is congruent to angle 2, then the measure of angle 1 will equal the measure of angle 2. And now I can go back and check out what expressions I have for this. All right, so angle 1 is 5x plus 8. It should equal the measure of angle 2, 8x minus 16. And now we can solve this out because all we're trying to find is the value of x. All right, so again, these are the places where I say if you've got variables on both sides of your equation like we do now, and numbers, the constants on both sides of your equation, I tell people to start with the smaller letter first. That way you've always got a place that you can start at to solve these out. So minus the 5x to both sides because 5x is smaller than 8x. All right, so 8 equals 8x minus 5x. Leaves me with 3 x's left over. Minus 16. Now we can add that 16 back. 8 plus 16 gives 24, which is equal to 3x. So to undo my multiplication, I can divide out by the 3. And my x is equal to 24 divided by 3, or 8. And there's my final. So again, that's using the congruent angle pieces that angle bisector is making. So now let's see what happens when we take our angle bisectors into the triangles. All right, so like before, we get that idea of concurrent lines. And so specifically concurrent lines, like it was last time, I'm going to zoom in here, 2 or more lines that are intersecting at the same point. And that one point that they intersect at is called the point of concurrency. So when it comes to your angle bisectors and triangles, when we draw these out, these are going to have to be drawn from the vertices of the triangles, and they're going to cut each triangle in half. And again, that's where the idea of making part 1 equal to part 2. So you're creating the 2 parts when you're cutting your angles in half. So let's say I draw one from the top angle of this triangle. So it's got to start at your vertex and cut the angle in half. So I'm not going to do it actually that long. And on either side of that, we get the congruence marks. If I was to do it from the bottom left vertex, oops, got off just a little bit. Again, we would have congruent marks on either side of that. Now notice I gave this angle 2 curves instead of just 1. That's to show that it is not the same as that angle up at the top. And then we have our third angle. So this one I'm going to give 3 to show that it is not the same as the other 2 angles. But those congruent marks for the angles, those arcs, those curves, those are where you're going to be focusing on your congruent pieces, your part 1 and part 2, because each of those 2 angles, those corners, now have 2 equal parts. So now notice that all 3 of those had angle bisectors. So we get what's called the incenter of a triangle. So the incenter is the point of concurrency for angle bisectors. So if we do the exact same thing that we did for the top triangle, this time I'm going to make the lines a little bit longer because all 3 of those angle bisector rays that I drew are going to cross in the same spot. Now, keep in mind, I am doing this free-handed, so I might be off just a little bit, but this is why we have the expression not drawn to scale. Okay, so there's my first angle. Now they don't have to go outside the triangle. I'm just doing that so we can see each of the different lines. All right, and there's my point of concurrency right in the middle where all three of them cross. So that is my in-center. So we do have some special properties that come along with that in-center. So the angle bisectors of a triangle intersect at, like we just found, at one point called the in-center. And remember, we talked about any point on the in-center was, I'm sorry, any point on the angle bisector was equidistant to the sides. So the same thing is true here when you're looking at in-centers with the triangles. It is still equidistant to the sides of a triangle at a right angle. And again, that means we need to look for the 90 degrees. So this in-center that we have, where it makes a perpendicular segment there to each of those sides of the triangle, is supposed to be the same length. Now, again, visually, it might not look like it right now based on my drawing. But again, remember, this was just a freehand drawing. So let's see how we can find out our missing pieces using the in-center. So looking at example 3, find the measure of angle JAC if point J is the in-center. So let's start with that, JAC. So we start at J, go down to A, and out to C. So I am looking for this missing angle. I'm going to color it in so we can find it easily. I'm looking for that missing angle. So one thing I know right away is it should also be the same thing on the other side. So we're only looking at your angle numbers right now. So that means I'm not going to look at the numbers that don't have that degree bubble. So I'm not going to look at the 12 and I'm not going to look at the 15. So one thing I do notice at angle C, these two angles have to be the same. So if one of them is 32, I can copy it over and I get another 32. The same thing is going to happen over at angle B. Those two angles have to be the same. So if one of them is 34, so is the other. So now if we look at the big triangle that's going on here. So let's say I redraw that triangle for a second. We've got A, B, and C. And let's ignore all the information that's going on the inside right now. At B, if we add up those two 34s, I have 68. At letter C, if I add up those two 32s, I have 64. So now in that big triangle, I really do have two angles out of the three that I need to figure out my missing third angle. So I can add those up. Which is 132. I can now take that 132 out of 180. So that leaves me with, leaves me with 48. Okay, and now remember, the entire large angle at angle A is 48, but I only need a piece of it. So if this whole thing is 48, I need to divide it by 2 so I can see what's going on at each piece. So 48 divided by 2 gives me 24. So there's 24 degrees at each of these angles. So then the measure of angle JAC (24 degrees). Again, because remember that 48 that we found was being cut into 2 parts. So now let's use this same triangle. I'm going to erase all of this out of here and do our example for our last one. So find JF if point J is the incenter of the triangle. All right, so this time we're looking for J to F. So in this case, JF is a length, it's not a measurement. And so this time I'm not looking at the numbers with degree bubbles. I'm looking at that 12 and 15 because I'm dealing with segment length. All right, so one thing I know, if when I'm looking at my 12 is all the way from E to A, while my 15 is all the way from J to A. So problem is, right now I've got a piece of a triangle here. I've got one side of the triangle and I've got the other side of the triangle. I don't necessarily know E to J yet, but technically I do. If I'm trying to figure out what JF is, oops, sorry, I'm going to change that color. If I'm trying to figure out what JF is, well, it's also the same as J to D, and it's also the same as J to E. Because remember, all 3 of those lengths to that perpendicular spot, that perpendicular point, are supposed to be congruent. So now, if I can find EJ, I can find JF. And right now, I have 3 sides of a right triangle. And if I have a right triangle, I can use Pythagorean theorem just like we saw at the beginning of the year. So I'm going to redraw only that one triangle. So I'm focusing on this triangle. So that's the side that I'm trying to find. I know my one longer piece here on the other side of the 90-degree angle is a 12. And that means the hypotenuse is 15. So now I have an A, I have a B, and I have a C. We can use Pythagorean theorem. So Pythagorean theorem was the theorem that said A squared plus B squared is equal to C squared. So if A is an X, then I have X squared. B was 12, so plus 12 squared. C is 15, so plus 15 squared. All right, let's solve this out and see what we have. So my X squared is going to stay in X squared right now. 12 squared is 144. 15 squared, 225. All right, now just like we did at the beginning of the year, now we can subtract out what we know. So minus the 144 to both sides of our equation. So my X squared is equal to 81. So now to undo the squared, the exponent of 2, that's where we can square root both sides of this equation. So I want the square root of X squared and the square root of 81. So the square root and the squared leave me with just the X. And square root of 81 is 9. And now I know what my missing length is supposed to be. So JF is equal to 9. Because if my side of X is 9, then it's 9 for all three of them. All right, guys, I hope you enjoyed learning a little bit about your in-centers. Please don't hesitate to reach out to me if you have any questions at all. Have a great day, guys.